In this video, we're going to talk about improper integrals. And colloquially, I think of improper integrals as integrals that go off to infinity. Now, this isn't a technical phrase, and there are a couple of ways that things can go off to infinity. But in some manner, the integral has something infinite about it. So we're going to look at the two possible cases for this. The first one is the case in which an integral has infinite bounds. So we're going to start by just looking at a concrete example. Let's suppose we wanted to look at the integral from 0 to infinity of the function e to the negative x. And in case you don't have an image in your mind immediately of what this graph looks like, I call it an airplane landing, that it intersects here along the y-axis at 1, because when x is 0, e to the 0 is 1. But it gets closer and closer and closer. It sort of dives downwards and gets closer to 0 as x goes out and out and out. And just looking at this, you would say, oh, well, this goes on infinitely. Shouldn't this just be infinite? And one of the cool results of calculus is that you can have things that are infinitely long, but they're so skinny that the quantity that you're adding up each time as you go out further and further becomes so infinitesimally small that there's a bound on the total amount of area that's created. I think that's sort of mind-blowing to think about. What is this region? This is an infinitely long region that ends up having finite area. It's not always the case. There are other functions that go towards 0 that don't end up having finite area, and we'll talk about those cases in a second. We'll look at another example. But because we're in calculus, we're going to look at a formal treatment of this. How can we formally define what's going on? What we're going to do is, instead of looking at the integral from 0 to infinity, I'm going to look at the integral as x goes from 0 to some fixed value r of e to the negative x dx. So visually what I'm thinking about is I'm thinking of the integral is going to start and it's going to go out to some value r. And really what I'm doing is I'm just examining what is the area under the curve from x equals 0 to r. And this is something that we compute really pretty easily, right? This ends up being, if you wanted to be technical, a really straightforward u substitution that I can let u be equal to negative x, because then du is equal to negative 1 dx. I don't have a negative 1 in this integral, so I'm going to multiply this integral by negative 1 and negative 1. So the negative 1 dx becomes a du. This is negative from 0 to r. Ooh, as x goes from 0 to r, I should be technically correct, of e to the u du. And I know what the integral of e to the u is. It's e to the u. And I'm going to replace back in the fact that u was negative x, evaluated from x equals 0 to r. So this is negative e to the negative r minus negative e to the negative 0. E to the 0 is 1, so minus negative 1 is positive 1. I can also rewrite e to the negative r as e to the r plus 1. So this would be for a finite bound. What did we do? We just took, instead of considering the infinite integral, which was our original question, we instead decided to just look at something finite that went to r. But because we are mathematicians, we are calculus students, what happens if r goes further out? If I picked a bigger value of r? An r that was out here. Or let's pick an r that's all the way out here. And we can consider what happens to the limit of this integral. And by calculus, we see that our original integral, the integral from 0 to infinity of e to the negative x dx is exactly equal to the limit as r approaches infinity of the integral from 0 to r of e to the negative x dx. For many of you, you might say, well, this is just semantics, right? Like, this looks exactly like this, that here we just had an integral from 0 to infinity, and now you replaced an r and said that r is going to infinity. The technical difference is very meaningful, that each of these individual integrals is an exact integral. You get an exact value. There's no estimation or approximation, that this integral is a finite integral with an exact area. So I have this sequence of values, these sequence of area values, and I'm seeing if this sequence of numbers is going somewhere. And so this limit is not looking at the limit of moving r bigger and bigger. This limit is looking at a set of numbers, and these sets of numbers sometimes approach one particular value. And in this case they do, right? We just computed this integral, and we found that this integral is equal to the limit as r approaches infinity of -1 divided by e to the r plus 1. And we have the tools from calculus to be able to evaluate this limit. What happens as r goes to infinity? That means that my denominator is getting infinitely large, so the value of this fraction is going to 0. When I evaluate this limit, this value becomes 0, and I find out that the area under this curve is actually exactly equal to 1. Now this, at least for me, is a phenomenal result. It's the idea that I could have something that's infinitely long that still has an area that's exactly equal to 1. Let's look at another case, and we're going to do the exact same technique as before. So, let's look at another example, one that has infinite bounds. So we're integrating over something. It turns out that this function, 1 over x, also shoots off to infinity itself, but we aren't going to look at that part of it right now. What does this function look like? You can graph it on your calculator. This is a classic example of the most basic of rational functions. It looks like this. And here we're looking at the integral from -infinity to -1, so I'm going to sort of chop it right here at -1. And we want to know what's the area back here, and we're going to do the same trick that we did before. We're going to say that our integral from -infinity to -1 of 1 over x dx is equal to the limit as r approaches -infinity of the integral from r to -1 of 1 over x dx. So in my mind, I can write this red r here, and I'm thinking of, for any fixed value of r, I can find this area. And we can compute this integral just as if we were doing normal integration. And what's the integral of 1 over x? It's the natural log of the absolute value of x. So this becomes, again, the limit as r approaches -infinity well, it's okay. The integral of 1 over x is the natural log of the absolute value of x, and I need to evaluate it from x equals r to x equals -1. Whoops, I should have done r in red. I was trying to be all clever and fancy, right? So this is equal to the limit as r approaches -infinity of the natural log of the absolute value of -1 minus the natural log of the absolute value of r, which is equal to limit as r approaches -infinity. I can combine some, so the natural log of the absolute value of -1 is just 1, and the difference of two logs is the log of their quotient. So it turns out that this is the natural log of 1 divided by r. So what am I doing here? This is a property of logs. This isn't calculus. That it's derived from exponent rules, that if I have the difference of two logs, it's going to be the log of their quotient, and I want the absolute value of that. So this is equivalent because I'm looking at the absolute value. It'll be the same as the limit as r approaches positive infinity of this value. But regardless, that's actually a minor point. So what is 1 over r as r approaches -infinity? 1 over infinity, that limit is 0. So this is the natural log of 0. And what is the natural log of 0? It's undefined. And what does that mean? It means that we just got an infinite result. So here's an example of an equation where we have our function is getting closer and closer and closer to 0, but when we went ahead and computed our limit, we found that our limit was undefined, that we got an infinite result. And the conclusion that we must draw is the fact that this integral, the integral from -infinity to -1 of 1 over x dx, diverges. That this area is infinite. So, unlike the previous example, here we're getting closer and closer to 0, and it's squishing fast enough that our area actually converges to a single value. Here, although my function is getting closer and closer and closer to 0, it's not squishing fast enough that this becomes a divergent integral, that I have infinite area between this curve and the x-axis. So those are a couple of cases, and those are the techniques. So what are the techniques? We're going to have to do integration like we normally do, and we're also going to have to evaluate limits like we have in the past from previous calculus classes. So like I mentioned, that was case 1, the case where I had infinite bounds. Let's examine case 2. Case 2 happens when I have fixed bounds on my integral, but the function itself is shooting off to infinity somehow. So like, I could have done this as an example actually. If I would have gone from -1 to 0, this is a place where my rational function is shooting off to infinity. That's also taking place here on this one. The integral from 0 to 8 of 1 divided by x to the 1/3, and I'm looking at it this graph looks a lot like the previous graph. It's another example of a rational function. But I'm examining what happens between x equals 0 and x equals 8. And we're going to do the same sort of trick that I'm going to set up a red r value. But this time, instead of r going to infinity, I'm going to have r getting closer and closer to 0. So these areas are going to get pushed closer and closer to 0. So let's look at that formally. So my original integral from 0 to 8, 1 over 1/3 dx. I guess first I should note 1 over x to the 1/3 is not defined at x equals 0. So in order to make up for the fact that this is not defined at x equals 0, I have to find which of my bounds is this not defined at, and that's the bound that I'm going to set r equal to. So I'm going to set r in place of the undefined bound. So I'm going to look at the limit as r approaches 0 of the integral from r to 8 of 1 over x to the 1/3, which I'm going to rewrite as x to the negative 1/3 dx. Thankfully, this is something that's easy to integrate because this is just power rule. So I'm going to raise up the power, and that becomes x to the 1/3 plus 1 becomes, x to the negative 1/3 plus 1 becomes x to the 2/3, and then I have to multiply by the reciprocal. And then I evaluate this as x goes from r up to 8. So continuing on over here, this is going to be the limit as r approaches 0. Plugging in the upper bound, I get 8. The cube root of 8 is 2. 2 squared is 4. Maybe I'll write this all out because this is hard for me to do in my head. Of 3/2 of 8 to the 2/3 minus 3/2 of r to the 2/3 which is equal to the limit as r approaches 0 of this value. 8 to the 1/3 is 2, squared is 4, divided by 2 is 2 again, so this becomes 6 minus 3/2 of r to the 2/3. And now let's go ahead and take the limit and see what happens. What happens as I let 0 be raised to the 2/3 power? Well, 0 to the 2/3 power is still just 0, so this whole term just becomes 0, and I'm left with an integral value of 6. That's a phenomenal solution. I think that that's really nice, right? That we just found that, again, here this function is shooting off towards infinity, and we got one nice, solid, concrete solution for how big the area is, even though it's infinitely tall in this case, before we looked at infinitely wide functions. Just like before, let's look at the second case again, only this time we're looking, so the integral goes from 0 to 2 of 1 over x cubed. Similar sort of rational function. We see that my function 1 over x cubed is not defined at x equals 0. It's shooting off to infinity. So I'm going to place r instead of 0 in the bounds. And I'm thinking of this picture, here's 2, and here's where my r value is going to be. And let's go ahead and set up our integral. So our original integral from 0 to 2 of 1 over x cubed dx is going to be exactly equal to the limit as r approaches 0, because that's the undefined bound, of the integral from r to 2 of, instead of writing 1 over x cubed, I'm going to write it as x to the negative 3 dx. Again, something super easy to integrate, just using power rule. I'm going to add 1, so this becomes negative 1/2 times x to the negative 2. and I evaluate that from r to 2. So that's going to be equal to the limit as r approaches 0. Plugging in 2 for x, I get -1/2 times 2 to the -2 minus -1/2 times r to the -2. Let's compute this value. Let's see, 2 to the -2, that's 1/4, right? Because 2 squared is 4, and then take the reciprocal. So this first fraction becomes 1/4 times 2, it's -1/8. And then I need to subtract out, I guess I add 1/2 of r to the -2 is going to be 1 over r squared. But look what happens here, in contrast to what we saw before, because this r is raised to a negative power, as r goes to 0, as my denominators get smaller and smaller and smaller, this limit has an infinite result, that this limit does not exist. It's an undefined limit, it's an infinite result. So this limit does not exist, and we get an infinite result. Why is that? In my head, I'm thinking to myself, 1 divided by something really small shoots off to infinity. This is what I'm thinking in my head informally, that as my denominator gets tinier and tinier and tinier, 1 divided into a multitude of pieces, I can get even more pieces, so this goes off to infinity. So this was a case where this is shooting off to infinity, it's getting closer to 0, but this integral, our notation for this is we say that this integral, the integral from 0 to 2 of 1 over x cubed dx, diverges. Let's summarize what we just talked about. These functions are really similar. The 1 over x cubed function is similar to the 1 over x to the 1/3, but the shape of those curves are a little different. And we can summarize this with something that we call the p rule. Now bear with me, the p test for convergence. This is common notation, and this looks like a lot, but I think that it's a good summary of how we can evaluate these integrals. Suppose that p is bigger than 1, and I'm looking at functions of the form, these are all for functions, integrals of 1 over x to the p dx. So an example of that was the example 1 over x squared. What does this function look like? It looks like a rational function, but as it goes off to infinity this direction, it gets squished really, really, really quickly. So if I look at an integral from a to infinity, I see that it squishes down quickly, and we can compute an exact value. It converges, and it converges to this, and we can do integration really easily to see that this is what it converges to. But if I look at what happens back here, as it shoots up towards 0, this area, although this function does get closer and closer to 0, it's too fat. It gets closer too slowly, and that's why we see that it diverges. When p is exactly equal to 0, we get the function 1 over x, and the function 1 over x is not skinny on either of the ends, that it's sort of a teeter-totter. As p's get bigger and bigger, this squishes faster and this expands. As it gets smaller and smaller, this squishes and this side expands. So this is my picture over here of it squishing and expanding. When it's exactly equal to 1, p equals 1, which is the function 1 over x, it diverges both directions. This is like exactly barely too big both ways. But as p gets less than 1, if it squishes in this way, shooting off to infinity converges or as the limit as r approaches 0, this area converges, whereas this doesn't get close to 0 fast enough, so this part diverges. So rather than memorizing sort of these sets of rules, I have these three pictures in my head. And I think when p is big, it's fat next to 0, whereas when p is small, it's skinny next to 0. And like a teeter-totter, where if it's skinny here, then it would be fat down here, and if it's skinny here, it would be fat up here. So in addition to our p-test for convergence, we also have a tool in our tool belt. Well, maybe I should say, because of this, we can look and know if something converges really, really quickly. That we could look back at this original problem that we just did, and I could say, aha, in this case, p is greater than 1, and I'm looking from 0 to 2, so thinking about picture-wise, from 0 to 2, that's looking at the fat part, so I know that it's going to diverge. Whereas without doing any work, if it were going from 2 to infinity, I would know that it would be convergent, because it would be in the green zone, where my p is greater than 1. Okay, so now finally I'm going to do the comparison test. So the reason why we like these benchmark functions, these p functions, is that we can start comparing other functions to them. And if my p function converges, so here are my examples. Let's call my green function f of x. And my red function, maybe it's a crazier function, g of x. And I'm looking at the integral from a to infinity. If my function g of x is smaller than my function f of x, if g of x is always less than my function f of x on the interval from a to infinity, and from a to infinity of f of x converges, we also have that the integral from a to infinity of g of x converges. Let's take a second to see what I'm saying here. So what I'm saying is that, let's say I have this f of x function is my bounding function. It's always the big function. It's on top of my g function. My g function stays smaller than it. If this integral converges, it means I have finite area under this curve, then of course you would end up with finite area under this curve because it's smaller than it, that this amount of area is less than this area. So I would know that the being bounded by a convergent function means that this integral must also converge. It doesn't tell you how much area there is. It would just tell you that there was less area under the g of x curve than the f of x curve. We can do a similar comparison in the opposite direction to prove that something's divergent. So let's say here our f of x function converged. Let's say that in this case our f of x function is sort of a fat function, and it's divergent. And we have some g of x function that's always above it on some interval a to infinity. So this is the opposite case. This is the case that if g of x is greater than f of x on some interval ab, or a to infinity, and we know that our f of x function diverges, then we must have also that our g of x function diverges. Oh, I missed the dx. dx. What's that saying? That's saying that under this f of x function, it's divergent. It means that we have some big infinite area under here. So if the g of x function is even bigger than that, of course that area would also have to be divergent because there's more. What this doesn't say is pieces in between. Like, let's say that f of x was divergent and g of x was under it. That doesn't tell us anything because we don't know how close under it is. It might be like really tiny down here, in which case it might be convergent, or it might be really close up here, in which case it might be divergent. That just being less than a divergent function doesn't tell you anything. Similarly, being greater than a convergent function doesn't tell you anything. So how do we use this comparison test in practice? Let's look at two final examples. Consider first an integral from 2 to infinity of 1 divided by the square root of x to the fourth plus 2. The first thing that we need to do is try to think about what functions are similar to this function that I can use usually a p comparison test with, right? I want to think to myself, well, what is the... So here's my scratch work. My scratch work says that the square root of x to the fourth plus 2, that's always going to be bigger than the square root of x to the fourth, right? Because I'm adding a little more to it. So no matter what, this is always positive, so adding a little more to something positive is going to make it big. And the square root of x to the fourth is the same thing as x squared. So if my denominator is bigger, that means that once I take the reciprocal of that, that's telling me that the reciprocal is going to be smaller. If I have a big denominator, that's a smaller fraction than if I had a smaller denominator. And this is what I'm going to use as my comparison. So here, my f of x function is this function because this is the one that I know something about, and I'm comparing it to my g of x function over here. And how do these functions compare? Notice that this integral, the integral from 2 to infinity of 1 over x squared dx, I can use a p-test on. Looking back, this is the case where my p is greater than 1. So I can look at my chart. Maybe I'll put it over here. Here I have x squared, so my p is greater than 1. So I see that if I go from 2 out to infinity, that this function is going to converge. And if this converges, and my function over here is smaller than it, so being smaller than something that converges means that this piece must also converge. Smaller than something convergent means that this also converges. So unlike this one that it's easy to calculate the exact integral, this I could do trig substitution and inverse trig. Anyway, it's a little messier than something that I would want to actually compute. But so this doesn't tell me the exact value of the integral, but it does tell me that it's convergent because it's smaller than something that converges. And let's look at our final case. So let's look at this final example of a comparison test. Suppose I want to know the integral from 1 to infinity of 1 over x to the 1/2 times the absolute value of sine of x. And really, all that I want to know is whether this converges or diverges. That's all that I can tell with the comparison test. I can't find the exact value of the integral. So first, let's look at this little piece, because 1 over x to the 1/2 is something I know about using a p-test. But we know that the absolute value of this sine function is always going to be bounded between 0 and 1, because our sine curve never gets above 1, and because its absolute value keeps it positive. So because of that, this thing is always some fraction, right? And so no matter what, if I take x to the 1/2 and I multiply it by something small, that's going to make it smaller than my original x to the 1/2, right? Because x to the 1/2 on its own, it would be equal, but now I'm multiplying it by something little. So if this is smaller than this, that means that 1 over this is bigger than this. So let's analyze some of the behavior of our comparison function. Let's go ahead and compare it with this function. So let's compare what happens when we take the integral from 1 to infinity of 1 over x to the 1/2 dx. This is nice because it's a p value that's less than 1. And I can see that for p values less than 1, I'm going from 2 out to infinity, that's going to diverge. That's the fat part on this function. So this piece, I know from my chart, diverges. And we see that our function is bigger than this function. So because our function is bigger than something that diverges, ooh, you're not going to like this notation. Somebody in math world is cringing a little bit. This function is smaller than this function, so it means that this integral diverges. This one has to diverge also. Because it's bigger than something that diverges, it must have diverged as well.